You may be just entering calculus, and you might be wondering, why am I even taking this class? Why am I learning this? Well, the truth is, the real world isn't static. In fact, quite the opposite. Our world is filled with constantly changing parts, which can't be most accurately described with pre-calculus. If you don't believe me, let's take a look at the most fundamental ideas in early calculus. So we have the derivative, so we're best to write neat, and integration. And I'm going to explain this using position and velocity graphs. So let's take at the first one, derivative. Let's take a look. So we have a graph of, let's just say, some particle. It's like some sort of cubic graph. If we're trying to find the velocity of this particle, which is, let's say, this is time, let's say y-axis is position. I'll write this in different color. Position of the particle. If we want to find the speed of that particle at any particular point, we would have to estimate using secant lines, which is essentially just using the slope formula between 2 points that are pretty close to that point you're trying to estimate in order to estimate that point. So I'll write it out, that way it's a little bit easier. So let's say we have this green point. Let me actually just choose one. It's a little easier. Let's say this green point right here. Let's say we wanted to estimate the exact speed the particle is traveling at that particular point. Now, if we're using pre-calculus, what we can do is we can choose points that are local, make a secant between them, and approximate. So let's say we picked a point right. We drew a line to connect them, and we did the slope formula right here. We would get a point we would get a value that's kind of close to the slope, but not close enough. Not close enough for a lot of things in the world which require great accuracy. Because look, let me say if I draw a red dot that's even closer. Let me actually redo that orange dot or orange line. Look how much our slope changes. That's a big difference. That's a huge difference. So it's just to show that we'd have to keep getting closer and closer and closer in order to get that value. And doing that with pre-calculus, it's kind of tough. Kind of tough to get something that's exact, but that's where we get into the calculus of it. And that's exactly where calculus comes in. So instead of us approximating by using a bunch of secants, a bunch of points that are infinitely closer, you see me drawing along those, and a bunch of secants. With calculus, we can actually get the slope at that point, at that particular point, and have a tangent line, that gives you the exact slope of that point. How fast, or what is the velocity of that particular particle at that particular point? No more estimating. It's the exact value. And that's why calculus is important in terms of derivatives and the differentiation process when it comes to finding the speed of particles. There's a lot of more uses, but for today I'll just be using the positions of particles, the velocities of particles just to explain. So that's why that's important. Now let's get to integration. Let's go down here. So now we're going to have slightly a different graph. So let's actually just make some new space. So let's go slightly different. So let's say this model, this is the same particle. So on our x-axis, we still have time. And on our y-axis, we have velocity of particle, our particle velocity. Now, why is calculus important when it comes to finding the velocity? Like what does this have to do with each other? Here, I'll explain it. So let's say we're trying to find How far has this particle traveled within a certain amount of time? So let's actually write out some numbers just to make it a little more visually easy to understand. So let's say this is time. Let's just say this is in seconds, just to make it easier. 1, 2, I know these aren't perfect. 3, 4, 5. Okay, so let's say we wanted to estimate after this amount of time when we're going from, let me draw like brackets, from time 0, time equals 0, to time equals 5. The question is, how far did the particle travel? Now, if we're doing pre-calculus, it's a lot easier. A lot of pre-calculus, or when it comes to problems that deal with pre-calculus, pre-calculus often assumes that our world is static, that let's just say it's more linear. So let's say if we have a graph that's like linear, or if we have a graph that actually has a slope of 0. I mean, that's what pre-calculus often assumes, that rate of change is constant. But, or however, as we see with this graph, our rate of change is not constant. We are changing at an increasing rate. So how do we model this instead? With pre-calculus, we could try to find areas along the graph, add up a bunch of rectangles, and that's how we can kind of approximate the distance that we actually traveled. And that uses more static world. Let me show you. So I'm going to draw some values. 1, 2, 3, 4. All right, let's say this is the velocity of the particle in miles per hour. Let's say we are at 10 miles an hour. This is 0, obviously. 10, 20, 30, 40, 50, right? So what you would do in pre-calculus to try to calculate this is you would use rectangles. So let's say at this point, this is about 10. Let's just say that for the sake of this. We would draw a rectangle at about that value. So we would assume for the first second that we were not changing, or rather, our velocity of the particle was not changing at all. We're assuming that it's static for the first second, which, although it's not true, but this is how we would approximate it. These are actually a thing called Riemann sums. And then we would do the same for the second particle. Let's say this is about, that's less than 20, but just about there. We would draw a second rectangle, assuming that the time from 1 to 2, right here, it had the same velocity. The velocity of, let's say this is about 15. And we do the same for the third rectangle. And we would do the same for the fourth rectangle. And the same for the fifth. Now, with this, we've kind of sorts, approximated how far did the particle travel. Because we can add up these boxes, because this is more pre-calculus, like I said, for each of these individual time slots from 0 to 1 second, from 1 to 2 seconds, 2 to 3, 3 to 4, and 4 to 5, we're assuming that we are not changing our velocity, that we have a constant velocity at these points. So with pre-calculus, we can add up the squares. So right, by multiplying them, because it's a square, it's a rectangle. So right here, we have 1 times 10. So the value of this rectangle is 10. The value of this one, 15 times 1, because that's the width, 15. Actually, let me write it above. Let's say this is 3 times 25. That's 75. And keep in mind, or actually, let me pause, because that might be a little confusing. Let me change this. It's not going to change anything about this. But let's say this is miles per second. When we're multiplying and we're making rectangles on our graph, we're multiplying the x-axis by the y-axis. So we have the velocity of our particle, which is in miles per second. So let's write that out. Miles per second times time. second. And what we get is our actual distance because second cancels out if you go back to algebra. Then you just are left with miles, and that's miles traveled. Just wanted to clear that up. Anyways, you can kind of get the idea here. You can multiply there, add up all the values here, and you can get your approximation for how far did the particle travel from time 0 to time 5. However, if you look at these rectangles, you have areas over the curve, which means there's a degree of inaccuracy involved. If we did any other kind of sum, let's say there's plenty of Riemann sum types. Let's say we did a left-hand estimate. We are now under the curve. So there's still a degree of inaccuracy. What's the issue? With this velocity of this particle, we can't actually tell how far it traveled. In fact, we can't even tell its position because of this. We can't tell it to a perfect degree because without calculus, we just can't do it. And that's where calculus comes in. With calculus, with a graph like that, we're essentially able to get all the area under the curve, all of it, to a basically perfect degree to where we actually get to answer the question, how far did the particle travel? That's amazing. Now you might be wondering, how does this work? I mean, how did we get here? How does the calculus differ? So how does the calculus here, oh, here and here, how does that differ from the pre-calculus here and here? Now let's do a thing called the limit process. And limits are essentially a notation that looks like this. So it'll be as like some kind of variable, so let's say h or something, approaches a certain number, like let's use a certain value. And here's why. I'll show you with each scenario. So let's go with derivatives. So let's say we have the particle again, like the particle position and time. Let's draw our graph once more. I think something like this. Okay, perfect. All right, anyways. So let's say we kind of have that green spot again, which this might be kind of close to it, might not. We essentially use the same pre-calculus process. We just add a limit to it, which I can totally explain in another video on what the limit process is. But today I'm just trying to explain to you why do we need calculus and why do we use it. So with the limit process, so like I said, or with pre-calculus, you can draw a bunch of secants, get closer and closer, and that's exactly what we're going to do with the limit process. So as our distance from the one we're trying to estimate approaches 0, which is essentially just finding the exact slope on this, as we pick a point that's closer and closer, we will actually just get the slope of that point, which is pretty amazing. And that'll just give you eventually, when there's no distance, when you have no distance between this hypothetical point and this green point, you essentially just have that point, meaning you are just touching one point. That's where you have your tangent line, which is great. It's perfect. Now for integration, let's say our velocity of the particle. I don't know why I wrote it out so much. And we also have time. All right. Instead of just adding, or essentially what we're doing is we're still using a bunch of rectangles, but we're adding up smaller and smaller rectangles to be even more accurate. In the original problem with integration with pre-calculus, we assumed that the velocity was constant for 1 second intervals. What if we had intervals that were infinitely small. Intervals that essentially just caught one little section where the velocity actually was the same value. So let's say we had like really small ones, and you could keep drawing more and more. But what if it got so small that you don't even have a box like that where you have no overlap over the line? Let me erase that. You have no overlap over the line, no no going under, and you essentially just have every single velocity point with infinitely thin rectangles, and you're adding up the sum of all these rectangles. And from pre-calculus, this is essentially just a series. So it's the series, which forgot the notation, or this is like the summation of the series, or like of a particular series. And essentially what you're doing is you're adding up infinitely small rectangles. And basically just be the limit as the sum of these rectangles, which I will, like I said, I'll explain what limits mean in another video. The limit as the sum of these rectangles approaches infinity. When you have infinitely small rectangles, so small that you actually end up just integrating the entire thing, just as I said. To a perfect degree, essentially perfect degree. So now we can know after, let's say, 5 seconds, we don't have this estimate. Instead, we actually know how far the particle traveled. Now, why is this important? Let's talk about the particles. Let's go back. Let's go to the integration part. Let's say we continued assuming for 1 second intervals along this velocity of the particle graph. We kept assuming that the particle is traveling the same speed for 1 second intervals for, I don't know, let's say a minute. Essentially, the longer we do this, the more over the rectangle we get. We essentially just keep adding up more and more inaccuracy. And if you keep adding up the velocity of that particle, how far this particle has traveled, the more and more you add them up, the more time that passes by, the more inaccurate we are. Now, if we're doing a lab tracking the movements of a particle, now the distance of the particle from us is completely different with these estimates compared to just using calculus to find the accurate place of the particle. That's huge. That's incredibly important. And for a variety of many reasons, I will continue to reiterate this, but in this case, it just has to do with the particle. Now, what if we're trying to find the speed of the particle? As I showed you earlier, let's actually just do a whole new. Let's do a crap. Secants are not exactly accurate, and I already showed you that. All it takes is slight differences. So let's draw a secant through these 2 points compared to the actual tangent line of that value, which is not too far off for this example. But if you see completely different trajectories. So essentially, to sum it up, why is calculus important? Let's write it once more. So essentially, why calculus? To put it simply, it's modeling an accurate world. In this case, we aren't using assumptions like in the integration graph of the velocity, where we aren't assuming that the particle just stays the same speed, because it doesn't work that way. There's so many different forces, there's so many different random collisions for this particle that it's just going to be changing. I mean, in most cases, it's not going to be traveling at the same speed. So we need calculus in order to model the most accurate. I hope this has inspired you to learn calculus, and I'll continue to make more videos on actually learning calculus, because I hope you're really eager to actually learn calculus now, because truthfully, it's a lot of fun because it's the real world around us. It turns math from something that's just memorization and something that's not too intuitive, and it's just why. It's like, why am I doing this? Calculus explains the reason. Calculus is the reason. Calculus is our real world, and if you want to model it, this is the way to do it. Thank you for watching my video. I hope you learned something today on why we need calculus. I hope I ignited a fire a little bit to be like, oh yeah, time to time to get serious, time to learn about the real world. I hope that happened today, and you know what? I hope I just inspired you to start learning. I'm gonna keep making videos like this on how to learn calculus, the intuition about calculus, how to use it in your day-to-day life, and just have fun with it. If you guys have any questions, if anything's unclear in these videos, please let me know. I'm always looking for any criticism to I hope I can be the best tutor I can be for you all and keep learning.